This is our second video of the chapter 1 real numbers. So this is the question. I'm telling you already, I have told you 3 questions. Now the question, use Euclid division lemma to show that square of any positive integer is either in the form 3m or 3m plus 1. Means क्या है, by use Euclid division lemma to show that square of any positive integer, this is square of any positive integer either in the form of 3m or 3m plus 1. For solution of this question we apply Euclid division lemma, not algorithm. We have to apply the Euclid division lemma. For this is the Euclid division lemma, a is equal to bq plus r. What is our b? Look at this. This is our b. 3. Here is 3 and here is also 3. So b is equal to 3. Suppose children, here is a 9. Both the places 9. Then we have also taking 3 again, because 3 is the multiple of 9 and the 3 and 9. Which one is smallest? 3 or 9? Which one is smallest? 3 is smallest. So we have to take here b is equal to 3. You know that the b is equal to 3, the remainder is always 0, 1, 2, less than 3. Remainder is always less than 3. Now we have to discuss the first case. When the b is equal to 3, r is equal to 0. We are taking b is equal to 3, r is equal to 0. Put the value into the Euclid form. A is equal to bq plus r. B is replacing by 3 and r is replacing by 0. A is equal to 3q. And now when you get a is equal to 3q, and now squaring both sides, because in the question this is the given square. So squaring both sides, this is a square, this is 3q square, we get 9q square. And we have to find here 3m. So we are taking 3 is common, and inside the bracket this is the 3q square and 3q square. We have to suppose m, because we have to require here m. So 3q square is equal to m, and we get our first answer 3m. Now we have to discuss on to the second case. B is equal to 3 and r is equal to 1. B is equal to 3, r is equal to 1. Replacing the value of b 3 here and r 1 here. B 3 in the place of b, we write down 3, and the place of r write down 1. So a is equal to 3q plus 1. Squaring both sides, a square is equal to 3q plus 1 square, and here we apply the identity. A plus b whole square, a square plus b square plus 2ab. Applying the identity, a square plus b square plus 2ab. So we get 9a square plus 1 plus 6q, and write down 9q square. 9q square plus 1 plus 6q. So write down first is 9q square, then after this is 6q. Write down second place plus 1. What is the common these two? The common is 3, and left out here is when you take the common 3, left out 3q square. Here also we are taking common 3, the left is 2q plus 1. This is again we are taking to the m, because our answer is in the form of m. This value is m, so this is 3m plus 1. We get answer second 3m plus 1. Now on to discuss on to the third case. B is equal to 3, r is equal to 2. This is the b is equal to 3, r is equal to 2. Replacing b by 3 and r by 2, we get a is equal to 3q plus 2. Again squaring both sides and apply the formula of a plus b whole square is equal to a square. Identity applying a square plus this is b square plus this is 2ab. So we get 9q square plus write down this is 12q in the second place, and 4, this is the 4, right in this place, this way, 3 plus 1, because our answer is in the form of 3m plus 1. So splitting this 4, 3 plus 1. What is the common of these 3? 3 is common, left out 3q square. 3 common from here we get 4q, 3 common from here we get 1, and plus 1 is in the separate place. This is you get again let this is m, so we get 3m plus 1. So we have to prove 3m or 3m plus 1 is our answer. Clear? So now we have this is the exercise real number, chapter 1 real number, and exercise now discuss on to the exercise 1.2. Already we have to find a wind up the exercise 1.1. Now exercise 1.2. This is the first of all, this is the fundamental theorem of arithmetic. The fundamental theorem of arithmetic means every composite number, you know that the composite number like more than two factors, for example 4, 12, 18, these are the composite number. Every composite number can be expressed as the product of prime is unique. Every composite number having the factor in the form of prime and it always unique, means 5700 factor. This is only using the prime numbers. First of all, we have the prime number is like this. This is the prime number 2, 3, 5, 7, 11, etc. These are prime numbers. So first of all, we are using 2, 5700 divided by 2, we get 2850. Again divided by 2, we get 1425, and then 1425 divided by 3, 475 divided by 5, 95 divided by 5, and at last 19 divided by 19, because 19 also a prime number. The factor in the form of 2 into 2 into 3. This is the 2 into 2 into 3, 5 into 5 into 19. You can write the factor in this form or write in this form. Both are unique. Either you are taking the first 3. Instead of 2, you are taking first 3, then the factor is also, this is 2 into 2 into 3 into 5 into 5, 19. Either you are taking here first is 19, then also the factor are these. It means the factor is always unique. Now the question is this: 12 raised to power n can end with 0. This is the question. It means that 12 raised to n. 12 raised to n ka matlab many 12s are there. 12 raised to n means many 12. 12 into 12 into 12 into 12. Many multiplication of lot of 12s. So the question is saying that when you are multiplication of lot of 12, at last digit is 0. Everyone know that when you multiply 12 into 12 into 12, we cannot get 0 at last digit, because look at this, 2 into 2, 2 into 2, 4 to the 8, at last digit is now 4 when you multiply these 3. So now in this question we have to check here 12 raised to n can end with 0. Ki many terms of 12 you multiply it and can you get at last digit is 0? We have to check it. For this 12, let 12 raised to n is equal to 10 into q. We have to taking one of the 0 here. Already we have to taking one of the 0. Now the factor of 12 is 2 into 2 into 3 raised to n. Here is n, so power is n. The factor of 10 is equal to 2 into 5 into q. Q, why we have to taking the q in this situation? Because when you multiply lot of 12, 12 into 12 into 12 into 12 into 12, so last digit is 0, something here also, and this is the q and this is the 10. So write down in this procedure 10 into q. The factor of 10 are 2 into 5 into q. Now compare this with this. Compare these two. Look at this first two. First two, you look at this in this situation, 2 is here. In this situation, 2 is there. This 2 is the factor of 2 into 2 into 3 raised to power n. This 2. This 2 is the factor of 2 into 2 into 3 raised to power n. Look at this 5, and here is not 5 is not there. So this 5 is not factor of 2 into 2 into 3 raised to power n. 2 is the factor, but 5 is not factor. If both are factors, then we can say that 12 raised to power n can end with 0. 2 is the factor, but 5 is not factor. So in this situation, 12 raised to power n cannot end with 0. Now the one more question is also here. Find LCM and HCF of 6 and 20 by prime factorization method. The factor of 6 are there. First we use prime number 2. And 6 divided by 2 we get 3, and 3 divided by 3 get 1. The same situation, factor of 20, 20 divided by 2 get 2, 10 divided by 2 5, 5 divided by 1. So look at this, HCF is equal to this 2 and this 2 is common. So common value is always called HCF. One more 2 also there. Here is also 2 and here is also 2. Again 2 and 2. One more 2 also common. So in HCF again we are taking into 2. So here is a single 2, this 2 and 2 both situation have the common, so HCF is 2. Now for the LCM, look at this. In this situation 2 is single time, but in this situation 2 is 2 times. 2 is 2 times. So maximum value we are taking 2 raised to 2. 2 times we are taking for LCM. Look at this. Here is 2 is single time. Here is 2 how many times? 2 times. So we are taking in LCM 2 raised to 2. Look at this 3 1 time, and here is 3 is not there. So maximum value of 3 is 1 time. So we are taking 3 in 1 time. Ajay, look at this 5. Here is 5, but here is not 5. Both the situation, how many times 5? 5 is 1 time here. So we are taking single time 5. So the LCM in this situation is equal to 2 raised to 2 into 3 into 5. One more thing is also telling you, here is 2 1 time, but here is 2 1 2 3 times. So we are taking here 2 raised to 3. Maximum times the value a digit we are taking. Now one more question also there, find the LCM of the two number 96 and 404. These are the two number and HCF is given 4. So find LCM. How can we find the LCM? Here is a formula is there. LCM into HCF is equal to product of two number. These two number product always equal to LCM into HCF. LCM into HCF is always equal to product of two number. This is the formula. We have next 1 or 2 question we have to verify this formula also. So LCM into HCF is equal to product of two number. Look at this, LCM is same, but is the HCF? HCF is given already 4. Here you put HCF 4. Product of two number means these are the two numbers. 96 and 404 are two numbers. So write down two number 96 into 404. So we have to find the LCM is same and HCF value of HCF is equal to 4. This is given HCF is equal to 4. HCF is replacing by 4 and two number are 96 into 405. For finding LCM, 4 transpose in this side, in this form multiplication form, and then goes in this side, it convert into the divide form. The 4 cancel 404, 101, 101 multiplied by 96, we get LCM 9696. So one more question also there. I am telling you this question. 7 into 11 into 13 plus 13 is a composite number. We have to prove this is the composite number. This is the one of the terms, and this is also one more term. These are the two terms. This term and this term are two terms. What is the common of this and this? These two terms. What is the common? The common, look at this, is 13 is the common. So we are taking outside 13. What is the common? 13. Look at this. This is the one term. This is also one term. What is the common of these two terms? This term and this term. What is common? 13. So we are taking 13 outside. 7 is left here. 11 also left. Same. When you take the 13 common, what left here? 1. 1. So we are taking 1. And 13 also here common. What left behind? 1. 1 already common. 7 into 11 we get 77 plus 1. This is 77 plus 1 78. Again you are doing the prime factor of 78. Prime factor, first we use 2, we get 39. Again but divide by 3, we get 13, and 13 divided by 13 1. And these are the factor. Look at this. 13 is one factor, 2 also one factor, 3 also one factor. Again repeat 13. But here is a 3 factors. 13, 2, 3. If a number having more than 2 factors, this is a statement, these factors other than 1 and number itself, these are the 3 factors. These are other factors, 1 and number itself. This is the number. Every number has the 2 factors already. Each and every number, for example 5 has the 2 factor, 1 and 5. Every number having 2 compulsion factor. You look at this 5, look at this is 5, 5 already having the 2 factor, it is 1 and 5. Same situation, this full number, this is full number and 1. These 2 factor already having, but the 3 more factors are there, 1, 2, 3. Every numbers having 1 except 1 and 5. 1 more factor is there, then it is composite. Here is a 3 more factors are there, 13, 2 and 3. So it is a composite number. So I am giving the homework also, so that show that 7 into 5 into 3 into 2 plus 3 is a composite number. This question is the same, you can handle the situation. Same procedure you apply this question. Find the LCM and HCF by prime factorization method. In this question you can apply this method. Already I have told you this question. Check whether 18 raised to n can end with 0. This is also question here. In this question you follow for this. If you have any doubt, already I have given you a phone number, and call me for doubt. Thank you.